All right. Video number 3 for this one problem. Let's wrap this guy up. This was f of x equals 1/8 x to the 2/3 times 9x squared minus 8x minus 16. First thing we're going to do is answer part A. See, we haven't even gotten that far yet. We were just setting it up. Part A asks for the intervals of increase and decrease. So just look back at the graph that we had. The sine graph that we did. The intervals of increase occurred for x values from -4/9 to 0 and from 1 to infinity. The intervals of x values for decreasing function occurred from -infinity to -4/9 and again from 0 to 1. Look back at that sine graph to answer part B, the local min and the local max. We have a local minimum at x equals -4/9. So let's evaluate and find the y partners. F of -4/9 turns out to be approximately -0.78. So the ordered pair xy equals -4/9, comma, -0.78. That's our local minimum. We have another one that occurs at x equals 1. So evaluate f. Now this is the original f of 1. You get -15/8. So the point xy equals 1, -15/8 is the other local minimum. For the local maximum, we got x equals 0. Evaluate the function, you get 0, so it's xy equals 0. So here we have our local minimums and our local maximum. Part C, let's find the intervals of concavity. Look back at the sine graph and you'll see that we got concave up for x values from -infinity to 0 together with x values from 0 to infinity. And we also make a note that there were no points of inflection, pi, because the concavity on each side of the x value, x equals 0, had the f prime of 0 equals f prime of x equals 0. We had the same concavity. Look back at the picture. We had the same concavity on both sides of that point, x equals 0. Okay, now we're ready to do the sketch. And we're not going to have any points of inflection, but we will have an interesting point that you'll see there. For the sketch, let's do a really rough sketch. And what's going to occur here is we have a cusp at the point 0, 0. See, that might have been one of our special points of inflection, but the problem was concavity didn't change on the left and right. So that makes it a cusp, and you'll see when we do the final graph, that's what happens. It's a sharp turn, a point. And then we have that minimum point at xy equals -4/9, -0.78, and we have concave up there. And we have another local, these are local minimum at xy equals 1, -15/8, and we have concave up there. Now you just look at that, put it all together in your mind, use your imagination, and we get the following picture. This is the graph y, x. All right, here's our point 0, 0. Here's -1 and +1 and approximately. And let's see, we have our low points, our relative minimums. We have our high point at 0, 0. Those are our intercepts. I think we figured those out in the early steps, the zeros of f. And we have our two low points, and that's our picture. We have concave up on the left and right, and we have our cusp at 0, 0. It's not differentiable there at the cusp, but they didn't ask us that. There you go.